afternoon. I'm a assistant professor in civil engineering and also one of the co-organizers for our ICON seminar, together with my colleague Patrick Hume from ECU, who is also organizer. So today we are very fortunate to have our first speaker from industry this semester, Mr. Jim Misener, who is, I was introducing as the expert of connected vehicle and vehicle communication. So you can see from his slide V2X, for those of you who are not or who didn't take my class, V2X means vehicle to everything communication. So it enables different vehicles to talk to each other and allow all those vehicles to share information. So Jim has been working on this field for 30 some years, as he mentioned. I just realized from Jim that he actually knows my advisor since they were both young, as he mentioned, back in the early 90s. And he has been working for Qualcomm for 10 years. For those of you who don't know Qualcomm, I assume all the Purdue engineers know what Qualcomm is, but I should definitely search that online. I think the most recent rumor is Qualcomm is going to buy Intel. I'm not sure whether it's true or not, but he has been the senior director at Qualcomm and also global V2X ecosystem lead. And he has been very active both in industry and academia. He has been serving on the board of governors on the IEEE IT Society. He established, founded the technical committee on SCE on CV2X. And as I said, he was with UC Berkeley, their Transportation Institute PATH program, and was their executive director before he joined Qualcomm. Was also advisor to Booz Allen Hamilton, the consulting company. And last but not least, Jim received his bachelor and master degree from UCLA and USC, the rival schools, which is quite interesting. But without further ado, let's welcome Mr. Misener.
Thank you. It's a pleasure and an honor to be invited here. And usually I start with a story that adds levity, but I want to talk about this topic in a serious tone because it's so serious. When I go into the slide deck, you will see that the thesis statement, the problem statement, is a safety-oriented problem statement. And I normally don't say this, but I will tell this group that why did I start working on V2X for safety? In 1998, I was doing V2X for other things like automated vehicles. One of my friends perished at an intersection. I thought that maybe with the demise funding, because there were vagaries of funding, kind of affect us as we do research, that I would focus on trying to do intersection safety and connectivity. And I've been doing that one way or another ever since. The idea is to solve the problem. And it won't be me who solves the problem. It won't be my generation, it will be your generation. So I'm hoping I can impart a little bit of history and what the problem statement is and what the future prospects is in this talk. So again, happy to be here. So this is how I'm going to split the talk, mostly about the safety problem statement, but mostly parenthetically, because there's other things that V2X can do, but we have to be careful. When you have a hammer, the world looks like a bunch of nails. There are other things that could redress or address the safety problem in our country and the world. Then I'm going to talk about how CV2X works. And I know this is a mixed audience. Some of you are really into radio access technology and some aren't, so I tried to toe the middle ground. But please feel free afterwards. We can go as deep or as shallow as you want. We can talk about transportation and the practical aspects of it, but it's very good that we get a fundamental understanding. Now, what is called sometimes pejoratively the radio wars, and during the radio wars, that is, the DSRC was the dominant dedicated short-range communication 802.11p standard for the protocol for the war layer 1 was predominant. It came along, and I became the poster child, and therefore I have a lot of darts on my images. But ultimately, we proved out the technology. We is the coalition, the willing, and coalition of willing, very importantly here, included the car OEMs who are going to deploy this. So they need to deploy technology they can use. And then day one deployment. Now, US DOT doesn't call it, Department of Transportation doesn't call it day one. We in industry do. And I want to define what day one means to all of us, because it's going to be a while when we get to the story. And then day X, because oftentimes you hear connected and automated vehicles, CAD, CAV. I prefer to say CV or AV for now. But as I said, I'm looking at a bunch of people much younger than me. And you can instantiate the CAB. And I'm going to outline at least what my generation, perceives as the problem that maybe you can overcome. So then I'm going to do the safety problem statement. A little bit of caveat here. It's global, and in many global regions is worse than the US. This is a very US focused presentation, but I'll make some reference. I'll start right now. CV2X is going to happen to India. Siam wants it to happen, and the OEMs want it to happen. And two-wheeler to two-wheeler crashes in India claim 26,000 lives. That's just two-wheeler to two-wheeler. It's happening in China. And a different radioactive technology is happening, and my job really is to shepherd it through the regulatory, the standards, spectrum, which is a different flavor regulatory, and then broad adoption, talking to road infrastructure operators and talking to car OEMs. So it's kind of a fun job, but it's a difficult job because it's not happening yet. The problem becomes more and more vexing. So you see these numbers, and I'm not going to read the slide, but let me just tell you something that kind of is I'm going to segue into a little bit later, is that at intersections, about a quarter of Americans who die on the roads die at or near intersections. About 50% of the crashes. Now that's not the totality of the crash problem. For example, you're driving down a country road between, say, here in Indianapolis. That's not a country road, it's a freeway, but single vehicle road departures are a problem too. And that's 50% of the crash fatality problem. So V2X is not a panacea. It addresses a portion of the problem, but really it takes a societal will that is a safety culture. It takes people who want to do the safety culture, no matter how unpopular it is, and it takes multiple measures. Those of you who are civil engineers know that it's engineering, enforcement, and I'm not a civil engineer, but it takes basically a total systems approach and education, let's say, in order to imbue the safety culture to start to address this. Now, NHTSA, National Highway Traffic Safety Administration, on the order of it now approaching 10 years ago, a little inside baseball, when I was at Fuzhou, we did this work for them, shows that V2X can address, be careful, 82% of the crashes. If the crashes are multi-vehicle and they're not impaired driving. So there are other things in the safety culture that we have to take care of, right? And so I mentioned single vehicle road departures. It could, and we'll talk about this a little bit later, but this is particularly good and important with multiple vehicle crashes or cars that violate, say, the signal control at intersections, and a few other things. There are other things that it does too, and I want to talk about equity for a moment. And many of these crashes are on high-speed arterials and feeder routes, and these are where underserved populations are. So particularly underserved populations do have a higher safety issue at and around intersections. So you say it's only for fancy cars, and yeah, but it's really for people who are not necessarily fancy. We're all fancy in our own way. We just got to take care of it. And also, if you have, and we know this, and the people who dispute this in the literature, that 50% of congestion is due to non-recurrent incidents, crashes, and non-recurrent incidents. So you start to improve the environment, and then you do something about RUSA, the green light optimal speed advisory. You can start to dial greens as you go through. It does have an effect, a very positive effect on the environment. So there are other ancillary benefits, and I'll talk about tolling a little bit later, but I'm in it for safety. So let me talk about how it works. So some of these slides start off pretty simple, but then they're going to get a little bit more complicated, but nothing that this group can't handle. So people have different definitions of V2X. And notice I say V2X a lot. The slides say CV2X. That's because CV2X has become mainstream. But it's cellular V2X, and that confuses people because they think it has to be through the cellular network. No, it's really LTE V2X because it's a time synchronized system. I'll talk about what that means a little bit later. And a bunch of marketing people didn't name it. I was in the room for a bunch of engineers named it. So that's the problem. So people don't quite understand it. Although the definition has gotten broader and much more ecumenical. So let's start on the upper right. This is vehicle to network. So that would be, for example, the modem that you probably have in your car if you bought a relative car. So that is the wireless wide area network, or the LTE or 5G modem that you have in your car. That is now V2X because, you know, X stands for everything, as we all But all the other modes of V2X that I showed are actually interfaces, roughly speaking, are direct communication or side link. So there's uplink and downlink, which is V to N, and there's side link, which is direct communication. I'm going to go into, I don't have a slide on this because it would be a really boring slide, but just basically how the protocol works is ad hoc broadcast, which means I don't have a session. All I do is say, here I am, nominally 10 times a second, unless there's traffic congestion, and then there is a congestion control that derates them. So everyone broadcasts their state vector. And if there's an intercept predicted in the future of the state vector for V2V, then the OEM can determine whether and how to alert. So the alert modality is up to them. All this is information. It doesn't actuate any throttle, brake, or steering because it could be tied to the motor. I mentioned that I didn't mention, but I will now. Some architectures actually incorporate both the side link, the uplink and downlink, and the same SoC. So it is not functionally safe, and that'll be the end of here. I'll talk about what it takes to be functionally safe to be CAD. So all it is an alert. Although the alert itself, as I mentioned before, could be highly effective. So we think about V2V, and that's what I'm giving you. Well, one more thing about V2V. I said state vector, but it has something else. If you're the Eagle vehicle, you know where you're going. So if the model is an arc of curve, you have a path prediction, and then you also have a path history. There's no other sensor that can reliably, if you have an exogenous sensor looking at you, it can't predict very reliably whether you're making a turning movement, what type of turning movement that is, except that you, as the Eagle vehicle, can. The other thing it does, and I show this intersection, is that, it's at 5.9 gigahertz. We'll talk about that a little bit later. But think about 5.9 gigahertz as something that just a few centimeters in wavelength. It will bounce. So there's multipath, which means that we can't bend light, but we can have multipath, and this actually works in a occluded environment. So it's pretty slick, perfect for intersections. So V2V is what we aspire to do. Some of us aspire for V2P. That's pretty hard. So think about, and I'm having a tough time, it's working, but to get vehicle OEMs involved. So, and they're all for it. I'll talk a little bit about this later, generally for it. But get a handset OEM involved, that's what V2P would be, right? Think about the channel congestion. Think about the fact that if you have GNSS on, you're going to drain the battery. So you're going to have misdetection. That's pretty bad. Think about position accuracy. You're going to have false alarms. It's a hard problem. So we try to skin the cat a different way. Sorry, the cat analogy. I have a cat. I love cats. But we try to approach the problem a different way. And we'll talk about that. But one way is to put them on bikes. Bikes behave a little bit more kinematically than, say, a person who walks, not that much more, but there's power too, power to wheelers, e-scooters. So we're working on that. But what is near and dear, and I'll talk about this later and explain it, is vehicle to infrastructure. So if the infrastructure, and they call themselves IOOs, just hint, if you ever go to a civil engineering firm, make an impression, just in an interview, say, on government IO, it's infrastructure over operator. So if they start to put this in and they realize benefits in advance of these broad scale safety benefits, then you have a hospitable environment for vehicle OEMs to say on day one that I'll refer to later, their customers will. So this slide says a lot. I belabored it, but I wanted to really point out what CV2X is in all its incarnations. This is just kind of emphasizes it. So, what you see on the right is V2X. So if I work for Verizon, AT&T, or T-Mobile, I index on this. I don't, and we Qualcomm like all modes of communication, all interfaces. But for safety critical, that doesn't go through the network, that uses 5.9 gigahertz that the FCC has given to us as a gift, I'm still working on that, is the side link, and that is for, if equipped, you will have basically the transmission of these will be free. Nothing is free because someone has to pay for the infrastructure and put it in your car, but you will have a low latency, very reliable, ad hoc safety message, or basically the ears that accompany the eyes that are in the car. So hopefully I bifurcated what it is going on. And then if you're an IOO and you run an advanced traffic management system, or you're doing TISMO, or traffic system management operations, this could be interesting to you because I showed the side link, and I focus a lot on that. I'll focus most of this talk on that. But if you put it in a system, what you have is hyperlocal information, that could be transmitted up, and then you have link and network information. And you will have that at good enough latencies for traffic control. So what you do have here is an end state that we all want. I can say that. Those of you who study this, those of you who want to apply this, you will have this type of heterogeneous connectivity, which is absolutely essential to enact any control strategy at whatever level of granularity. So this would be the end state.
But I have a question. So you mentioned about the bandwidth issue and how you want to optimize it. So I think of it from an encoding perspective. Right now, if you want to move out to AV1 codec and encoding compression algorithm, but Qualcomm right now doesn't support AV1 even on its cell phone, where it should be able to. So why not use AV1 or some other codec which compress the volume much more than that, and the bandwidth would be safe?
So this is a different problem statement you're talking about. I'm talking about ad hoc direct communications, where we're just the way that we solve. So there's this legacy. This is not Qualcomm.
Yeah.
This is basically the vehicle safety communications industry,
Okay.
which has tried very much to have compact messages that only do ad hoc broadcast. So this is not about a codec or anything more complicated. So it's just nominally our messages are 300 bytes, and half of the payload, or a third of the payload, is the security header to do certificate management, so that you can instill trust or at least authentication as the source. So there's a lot to this right now. So we haven't even even discussed anything more than that. So this is just again the state vector, the security header, and to be as sparse as we can and to have a congestion control protocol. It's as simple as you can ever make. Very lightweight.
So nothing video, no transportation, no communication of any kind of video data.
No video data. We're talking about, so just to get into bandwidth, and I'm hoping that people can hear your good question. But what we're talking about in the US is 20, actually nominally 30, but these CV2X transceivers work at 10 or 20 megahertz channels. So you're talking 120 megahertz channel. And you could be talking hundreds of vehicles in the surround. So what you're trying to do is, that's what I'm talking about bandwidth. So you're just broadcasting ad hoc. You don't have enough bandwidth to do raw sensor data sharing. You only can do basically an abstraction of the vehicles. And actually, I'll talk about this later, about intersection. All right. So this is so you know, there won't be a quiz afterwards, but 3GPP is an important thing just to remember. Those of you who are not in standards, if you ever get in communications, 3GPP will be something you dream of, right? So it's third generation partnership project. So now we're like, you know, way past third generation, but names stick, right? If you're given a name at birth, you might like it or not, but it's gonna stick. So what it is, the global specification is so important for interoperability and telecommunications. Completely different than IEEE, but this is what the network operators and their suppliers live and breathe on. And there's an update every year and a half. So release 19 will be the advent of 6G. I'm talking here about release 14 and 15. So I'm talking even pre-5G. There is a 5G version that I'll talk about a little bit later toward the end. But 3GP why is it so important? Because OEMs are global. The modem that they specify that reaches out to the network is a 3GPP specification. Cars don't get replaced as much as handsets when they're really, really rich. So the cycle of development is slower. And if you have a safety system in the car, it kind of sticks. So it's 3GPP, release 14 at band 47, which is 5.9 gigahertz, is what we work on. It's mostly harmonized globally. I'm not going to criticize FTC, sorry, FCC, who could be on this call for us. But they're working slowly, perhaps imminently, to give us the final rule for the 20 megahertz so that we can apply this 3GPP technology. They have already said it shall no longer be DSRC. And I'll talk about the so-called radio orders when that happens. Single channel operation. Why is that important? In the DSRC days, and by the way, I was one of the original DSRC researchers, and it was multi-channel operation. So you had 70 megahertz wide spectrum, and you would basically have a control channel and then various service channels, and one would be an always-on safety channel. So you think about this. To get to the control channels, like we're all in a room. We go to the next room to listen to the instruction, we all get back to the room. So basically, we'd have this duty cycle problem, and that's not very practical, and it also requires the OEMs to put in two radios. Always on safety channel one that does multi-channel operations. So the 70 megahertz of spectrum that you hear that we lost, it's not good. More spectrum is good for some things going into the future, but it wasn't going to fly. This is one of the reasons that DSRC was not popular. So I'll talk a little bit more about that. Car OEMs are, they're making mass market cars and pennies count. These are major dollars to do. So single channel operation is pretty important. Those of you, and I'll belabor this a little bit later, who are into 3GPP, there's something called PROSE, priority and preemption, which racks and stacks applications. And depending on the channel busy ratio, what you do is those that are least important fall off the table. So there's a way, in addition to congestion control, rate control, that we apply. If we can do power control, we just do rate control. And in addition, and also a way of doing basically selecting what applications are highest priority in real time, we're able to do a lot of services on one channel. It's pretty important. And it's of course the ITS cases. So though many of you know the OSI model, right? 7 layers. And so the layers 1 and 2, with a little bit of work, can be used. Middle layers can use application protocols taken from prior generations. So the US DOT and a variety of OEMs have been doing V2X with DSRC research. I have been doing that since the 90s, right? Those proven protocols work just fine with a little bit of work. This is why we established the CV2X Technical Committee. And basically, we found a way to have an access layer in between and have the proven applications that we want to include intersections to work with the different radios. So I'm going to get to the radio wars a little bit later, but you can see this. So there's some arguments here. Enhanced range and reliability. I have another one, but I'll spill the slide, but I'll spill the news a little bit earlier. So that's a 7 dB loop margin inherently. Why? Because it's more energy per bit. So 7 dB, what does that mean? Many of you are electrical engineers, but let's just put it abstractly for those of you who aren't. In a flat Earth, no such thing, but a pool table, it's about a factor 2 range advantage. That's pretty good, right? Now, intersections, you don't really have to have a lot of range or work slowly as congestion, but it gives you higher reliability. And I'll talk about energy reliability for a given range. So it's a better radio. Link margin is just kind of hard to beat, right? So it has that. Actually, I remember this was a German stakeholder who said, well, what about trains? Something I want to put on trains. So we said, okay, put on a high-speed train, put on the Autobahn. So we designed in 500 kilometers an hour support. More cost efficient than other technologies. That can be argued, but an architecture that combines both the UU, that is the interface to the network, PC5, that is direct communication, is inherently cheaper, right? One device is cheaper than 2. So, but there are arguments both ways. And forward compatible evolution path to 5G. That may or may not be true because, as you know, standards take on, you may not know, but now you will. Standards take on a mind of their own because not a single entity controls standards, it's a community. But one thing that's really important here is the deterministic resource scheduling. So let me just go into a little bit about the differences in radio. I'll keep it fairly high level. But basically, 802.11 protocol is listen before you talk. CSMAC. Very polite, right? You listen. I try to teach my kids to do that, right? But another polite way is a reservation-based system. So it's not time synchronization. So that's the difference. But we have figured out as a community how to use GNSS. So you can have semi-persistent scheduling based on GNSS. So that brings in vulnerabilities too. And it brings in, I'll talk about this later, a very, very accurate GNSS that you have to have, but that's within technology. Guaranteed latency performance, and I'll expand on that a little bit later. And then the enhanced congestion control. That is a feature that was built in 3GPP, but upper layer protocols have our own. And I argued successfully that we shouldn't use the 3GPP one to make this more acceptable. We should do something just like the DSRC. So back to the points I try to make people. This goes a little bit deeper. It's synchronous. That's so key. So you need time for synchronization and frequency stability. So basically, you have to have timing within 391 nanoseconds. About 10 years ago, that was like too hard. These days, for example, I'm not extolling a particular company, but I work for one. we offer our package in a GNSS system that has this. One of our chipset competitors connects it to another GNSS system to get this timing accuracy. 3GPP has 4 basic synchronization sources. So, again, I told you I would get slightly deeper as I went along, but one of them, mode 4, is GNSS. We're talking 5G, it's mode 2, but that's in the noise. Node B, that's a beta cells power. That's how basically the phones generally work. You need a traffic copy saying you go at this time, you go at that time. Another is SLSS, which is side link synchronization system. This is pretty cool. We just introduced this finally at much hand reading. I'm reading my hands now to illustrate this into standards because if you go into a tunnel, you don't have GNSS coverage, you're messed up. DSRC isn't, right? It broadcasts at a clock and listens to other traffic. But if you have a way to index timing, you can basically, and very simply, because the ranges are prodigious, daisy chain. So if you have a roadside unit that's connected to can see the sky, you're good in tunnels. And just a little story. There's a big deal in Korea. Those of you that Korea knows the land of tunnels, and they've chosen CV2X. There was a big shootout for a year, not real guns, but technology shootout for a year. And in the end, we decided that SLSS is perfectly fine. And we is the community that includes the people who are favored of DSRC. So I'm going to talk a little bit about the guaranteed performance. So resources, a resource block is a resource pool is time and space. So basically, you try to grab each of those. So the innovation here, it's simple once it's explained, but it was innovative at the time, is that you measure the energy very quickly, and you look for whatever resources have the lowest energy. They're probably, but not guaranteed, to be further away. And you grab those. So you will never have you'll always be guaranteed a resource because you grab the least energy. What happens though, if there's a lot of people using the resources, the range gets smaller and smaller. You're always guaranteed channel access via this system. So you just choose the lowest energy blocks and you go. So this is a fairly in the noise, but very important protocol distinction as to why this works reliably. There's going to be other definitions of reliability. So that is the quickest I've ever explained the technology, and I glossed over things, but hopefully you get a feel for it. More than just it's a radio that broadcasts. So let me just go to a higher level right now. The gentleman has a question.
Is it more like a cognitive radio thing, the accessing the channel resources? Like you bring out which one's available?
You can call it that. I wouldn't call it that fancy. It's just a protocol, but there's some real-time adaptation. I didn't describe HARC. There's HARC here too. Actually, this blind HARC, which means a simple repetition, right? As you know, and you have kids, some of you do, some of you were kids. If dad or you said something twice, it's more likely to be heard. So that's what HARC is, blind HARC is. But there are ways of doing HARC that are much more selective. So yeah, it has a lot of other bells and whistles, but I didn't want to go really deep because I know it's a broad audience members. But happy to go to answer those questions offline. So that's basically the radio. So I talked a little bit about the applications, and I'm going to segue into why vehicle infrastructure is so important. So the holy grail and what OEMs have tried for, say 2016, we were very close to a mandate on DSRC. Okay, and then of course Qualcomm's sprung to action, and so did the OEMs. But that's a different story, and I'm talking about those radio wars. That was vehicle to vehicle. So the idea is that you put it on all vehicles, so it's a vehicle-led deployment. So that mandate, for a myriad of reasons, died. But that would be something we shoot for. So obviously we want VRU or VP protection too, but that again is explained pretty hard. But just imagine this, and I've said these numbers, they're very simple. Let's imagine that someday in 5 or 10 or 15 years, we get a 10% market penetration. Remember, you have an existing fleet, right? My cars are old, some of you guys' cars are old. It's going to take a while to get that market penetration. You have a 10% market penetration. The probability of you encountering another car is 1%. So being a vehicle is going to take a long time to really happen in mass to start having a significant safety effect, right? So that's what we want to do, but that's not what's going to happen first. What's going to make it take off is V to I. I told you a snippet of a very personal story about intersections. I was one of those that wanted to do intersections. It's a really hard problem statement, by the way, because now you're talking about traffic controllers and interfaces of traffic controllers and standards that SAE people don't even know anything about. And traffic controllers are dynamic, right? Demand responsive or actuated. Sometimes they have different timing plans. So you have to kind of measure the state of the traffic controller. And through careful crafting of standards, you can bring this out to something called SPAC, signal phase and time. So spit that out. Then we provide a map, which is a simple representation of the lane boundaries and stop bar. And that's broadcast. And also, we're working on, I happen to be the chair of this. I got looked into this in my copious spare time of an RTCM standard or RTK standard. So it's broadcast RTK to give you lane level accuracy. We're almost done with that standard. So that would be the red light warning violation. So that still presumes a lot of cars have this, right? But it is an alert. If you have this, OEMs who sell cars to consumers who want to have a safety effect, they're spending extra money, want to see safety. If you have this, it's already out there, the consumer starts to get benefit at their day one. And I'm going to belabor this later, there are other day ones. So think about a closed system. If you have a public fleet, say ambulances or fire trucks or police cars, you can equip and do preemption for ambulances, for emergency vehicles, or you can do priority, slightly different flavor. Those are your transportation for buses or freight signal priority. So if you start to find benefits for the fleet that the public sector owns, you start to get public sector wanting to build these, which build up into cars using this as long as we're very careful about the quality of the installation, the standards, and the profile. So that's kind of where it is. So I know this bottom line CV just to enhance, specifically enhance safety, yes, but there's more to it. There is a glide path, and that glide path is known. Will be known to you shortly. But let's talk about vulnerable road users a little bit. I said it was too hard. It's too hard if you think about it conventionally, but many of you are creative engineers or on the way to becoming really creative and well-educated engineers. So think about this, is that if you're given a problem that's too hard, maybe you can repose the problem and start to address a part of the problem. So certainly what we see in the upper left side, VRU at a blind intersection, hard on a handset, a little easier on a powered two-wheeler, still hard. School zone protection. So we've done this with Audi and Alpharetta, Georgia. Remember, the FCC has to still say yes and meet day now. So it's not a deployment, it's still a pilot. Or when school children board in the light, school buses, and the stop bars go out, that will send and receive a signal, a very simple standard message. So that's another way of addressing vulnerable road users. In fact, these are the most vulnerable. These are our children collectively. Another one is work zone protection. Now, there is, and those of you who are familiar with USDOT doing the tremendous things, a work zone data exchange standard, and on and on and on. But you know, I can learn about a work zone a mile in advance through my LTE or 5G radio. But as I get closer, I still might be a bad driver. And so you can geofence that pretty easy. And if the put a sensor there, and if the work zone worker starts to transgress toward the edge of that, you can provide a direct communication. So I'm going to show you a video. I think industry speakers always have to have video.
Work zone roadside safety messages offer a greater awareness
I'm
to
going
the
to yell
driver
over
who
this.
can receive
This is
an
via
initial
the
advisory
network
message
interface.
communicated over a cellular network.
And
Subsequent work zone safety messages via low latency direct.
so as you get closer, it transitions to
Vulnerable
direct
maintenance
communication.
and construction personnel in work zones benefit from CV2X as well. In the event that a worker wearing a smart vest
Doesn't have to
near
be a
the
smart
boundaries
vest.
of their work zone as a vehicle approach, work zone roadside safety messages offer a greater awareness to.
So I think you get the message here. Sorry, that was an unintentional pun. But the point is that network communication, which has latency issues, costs, can still work in compatibility with CV2X, and you can start providing vulnerable road protection. So this is only a part of the problem, by the way. IOOs, remember I taught you that term, if you didn't already know it, these are their people who are perishing on this side. So this is a very important problem, not just societally, but very specifically. Okay, so what I've done, just to recap, is I've described the problem, I've described the technology, and I've described the technology now at the upper layer of those. So, I'm a believer, but it's really good to be dubious. And so the entire community was dubious. So we had to prove it. So I think I've already said, I promised you that I would say already that the 7 dB link advantage, I think it shows up here. But think about this intersection. Keep on going back to intersection. This is particularly vexing because you see the canopy of trees. Those of you who know GNSS signals know that blocks. It blocks 5.9 gigahertz too. You've got non-line of sight. This is a difficult problem. So, but this is what we're trying to address. Again, if you don't have a really good GNSS signal, say you're in Manhattan, RTCM, RTK correction not going to help you, but you're usually not in Manhattan. So this starts to work, and we thought as a community a lot about how to address intersections, particularly like violation warning, but also any turning path. So those of you who do left turn across path opposite direction, that you have a green ball, you're turning left, that can be addressed here. So this is what we thought about quite a bit, is how do you enhance intersections? So I did some work. So we here, so you see just a list of folks and some acronyms that may not mean much to you. The 5G Automotive Association, I'm privileged to be a founding member on the board. There's 135 companies, telecom and suppliers, and automotive and suppliers, period. So it's a certain cadre of folks, generally highly technical. It's a German trade association, so imagine there are a lot of rules, but whatever. We did a technical assessment. Who is we? Who provided the technical muscle? Ford and Qualcomm. So what we did is we did our shootout. So we showed the advantage, and I'll show you a little bit of what some of the advantages are. The CAMP. CAMP is another acronym, Crash Avoidance Metric Partnership. So it was started by Ford and GM, but other OEMs joined from time to time, and it's pre-competitive research. So Ford and GM said, okay, Qualcomm, join us. So we're the first non-OEM partner in CAMP. And we did measurements, and we published a really thick report. I think it's 196 pages, but it's PowerPoint. Those of you who haven't been out in the world know that engineers and industry talk in PowerPoint, not necessarily the subject verb object agreement. So we did this, and we showed lots of data, and the conclusion was this radio technology works great. 5GAA, we wanted to show the comparison, and CAMP, because it was run by politicians, we were just saying it's good enough. But if you read between the lines, this really works well. Then we did what's called a capacity evaluation. So what we got is, those of you who are in telecom, these are GUIs, these are equipment. So these are devices. We got these devices, we call them super GUIs. So that each device would broadcast 10 times as much. Very hard to do with this reservation system, but we figured out how to do. So we emulated lots of channel congestion. And what we wanted to show is that this responds to the congestion control protocol, so it could work at scale. And then there's a whole bunch of global plug tests and verifications entity called OmniAir Consortium, which does certification. We're on the board. So obviously we at Qualcomm are doing all we could do to make this ecosystem better. I wanted to give you a few, I know that for the most part you're engineers, so we need plots, right? I don't have equations, I apologize, but I have some plots. So intersections is good, right? I talked about congestion control, and then this V2V, this nirvana, this ultimate state that we want to go to. So one way to measure the goodness is of reliability is packet error. So if the packet error rate is near 0, that means you're getting good transmission. I talked about nominally the packets of 300 bytes. We try to keep them small. If you have big packets, there's a higher packet error rate. We actually, those of you who are really into ERP, we're allowed to transmit up to 27 dBm. FCC has said on a certain condition be 33 for ambulances. We had to detune this because we were outrunning this test set. So we were at 18 dBm. You can see we're getting ranges of 900 meters. With HARC-on and 365 bytes, and then we threw, 1,100 meters, then we put in a larger packet of 1,400 bytes, and we're still getting prodigious range. Third line of sight, this is the middle of Michigan, not a problem. So let's emulate an intersection. So you can see that we included input blockers. This car is the crossing path car. We're still getting reasonable range. So think about an intersection. You're going to be going 15 meters a second, 30 miles an hour max. So if you do 15 meters per second with 30 meters, you still have 20 seconds time collision there. That's more than enough. In fact, that's overkill. So works pretty good at this. And we have more data than just this. And then we did the congestion control that I explained briefly earlier. But the data shows here that if you have basically congestion control or no congestion control, that the message counts received is pretty high. Congestion, no congestion control derates it. There's more to this data, but the point is that congestion control protocol specified in SAE works. So we have a chance to scale it. US DOT, being guardians of our safety, thought that we didn't do enough, so they put thousands of things. They got the same results. We told them. So there is plenty of evidence to show that the radio for vehicle communication safety is just fine. So these were the radio words. And earlier in my job, about 4 years ago, this was like all I did. Now I give fancy speeches to smart people. So it's a little different now. It's more advocacy. But the point is that we believe we should. Now, again, they're doing a shootout in Korea. We're trying to avoid a shootout in India. And China is a slam dunk because we're telling folks at India, North and DOT, that's the Ministry of Road Transport and Highways, DOT, which is the Department of Telecommunications, that, hey, it's plenty of global data. Physics is the same in India, so it's here. So we're trying to avoid that and other OEMs. But the point is that in China, by the way, slam dunk, this is the technology of choice. No argument, discussion. And again, forget about geopolitics, focus on safety of humans. And that's a good thing that's happening there. Something else to tell you that's just a little bit of inside baseball again, is that the protocol stack in China looks and smells almost like the US protocol stack. So that means global OEMs who are getting experience in China will have that type of experience to apply in the US. That was deliberate by the community. Again, we want to be ecumenical here. We want this to happen. So now I'm going to switch to a different part of the talk. You gentlemen in the black shirt, you have a lot to say.
You had a long range. How do you deal with interference in this kind of situation?
That's a great point. By interference, you mean multiple, because interference itself could be an antenna, but at the vehicle. Yeah. So no. So basically, there's no such thing as a 2 pis for radio antenna. There's no such thing. So, we do get noise from others. But if you think about the applications, they're really not for range. What we're trying to do is to have a higher link margin, which can be shown by range. But what we're trying to do is to show that the application will work. So you can do things like identify the car. But again, this is a criticism that's actually a good criticism. If you have a radio that performs really well and just blasts, then cars that are just not even in your surround, they don't matter what you do. The congestion control test addressed that. I'd be happy to take that offline, but it just adds channel congestion. What you do is you derate. So you have a rate control. That's not great either because that inherently adds to latency. There's no perfect thing, but we've shown this in large quantities. So basically what we want is high packet reception reliability at or near intersections. Over and again, focus on intersections. So now on to higher level stuff. Starting to get, so there's policy mixed in here and there too. This is a long, and those of you who've been in the Bay Area, it's a long road. If you go to the other side of the tunnel, it's bright and shiny. So, there's a lot here. This was a long struggle that the community worked on. But what I'm just going to draw you to, so and standards are a big part of this. So, but what's really important is that in July, very recent, right? The FCC chairwoman put out a PR that they're going to do the final rule. As we know that there is a correspondence vote happening right now, and we anticipate that final rule will happen. What does that mean? Right now, if I'm an OEM, I don't want to put out a device that transmits if I don't even know what the compliance is with FCC, and it's quote unquote illegal, right? Unless I get special provisions. So I'm not gonna do it because that's been really a headwind. It's like a hurricane headwind. But so this is imminent. So the other thing that's imminent, or that actually applies to my next slide, is US DOT. After much deliberation, it came out with preliminary plan about a year ago. Now they have a final plan, how to deploy. Remember when I said that they play a heavy hand because the infrastructure has to be equipped in order to entice the OEMs? So this is significant. So these are two really significant things that are happening. So we're really near the time, we're really near the end in terms of having no barriers to deployment. Something else that I'll harken to a little bit later is that 5GAA did a US deploy guide. So keep that in mind. I led that project. I'll tell you why. Hopefully that'll become clear. And then, of course, there's all these standards organizations that have worked pretty hard, and it's complex. Maybe I should have shown this slide first, but you can see that it's complex. And by the way, you can't just rinse, repeat, wash every time because every region has different dynamics. And for example, if you're in Northern Europe, you probably go heavily on using the network operator. That's land of Ericsson and Nokia, after all. If you're in Central Europe, you like ESRC. In China, you like CV2X. In the US, you like CV2X. So it's complicated, but it is what it is. And I'm not advertising for folks to have my job, but you can see the job is kind of fun in a certain perverse way. So this is what you can read the deployment plan, but this is the Reader's Digest. So this will save you reading. But if you look here, it's infrastructure led. That's important. And if you look at shorts of, I'll tell you what's bad, it's 12 years. In industry speak, 12 years is like forever. And the other thing that's bad is that, hey, there could be 3 presidents, theoretically, between now and then. And the transportation reauthorization happens circa 2026. So where's the money, right? Show me the money. But US DOT, public sector, don't stick their heads out unless they have a lot of confidence. So right now, so let's look at short term. They're funding it out of discretionary grants from the IIJA, basically the Infrastructure Act. And so discretionary funds are basically like how you compete with grades. Those who are really good get the A or get the funds, and those who are not competitive don't. But this thing has to be spread like butter smoothly in order for it to get this kind of network effect. So it needs to turn the corner. So people are working on how to have a long-term plan. So 25% signalized intersections, 40% intersections, and 85%. That's a prodigious amount. So doing simple math, this is $5 to $7 billion. That's my math. But if you think about this, the federal aid highway program is about 60 billion a year. And if you amortize over 10 years, it's really not much, but it still takes resolve. Some states have resolve. So Georgia DOT, for example, is putting in all their state intersections. A pretty good, decent population. Some states are moving toward that. But federal money is going to be key. There are 3 CV2X accelerator awards. That's just the tip of the iceberg. What I haven't said is worth pointing out is that it would be, I don't have this, so it's worth pointing out is that the 100% of the national highway system would be covered. So what does that mean? So the national highway system is key strategic roads and the interstates. That may be covered by the network communication. But the idea is to get full coverage so you get some benefit depending on the degree of safety. These large scale deployments, you see 12, 25, 50, there are criteria for it, but these are viewed as equal compensation. Much of transportation funding happens through the federal source. A lot of it is local sources too. There's a whole bunch of problems in here that we can collectively solve. And how do you educate the workforce? How do you have operational maintenance budget? There's a lot of detail. And the news, I'm not saying it's good or bad, it's 2 OEMs, 3 OEMs, 6 OEMs, that's not a lot. And 20, it's conservative. But the idea is, and I've used this before, so those of you who heard me say this before, I apologize. Feel the dreams, right? If you build it, they will come. So this is kind of it's infrastructure led, but various entities throughout the U.S. are cheering this. So again, I talked about this. I won't talk. So I'm going to talk about this deployment guide. said I'll talk a little bit about this. It's industry initiated, but what it's saying in short is that if I'm driving a car in this county, I get some messages that I don't care about. If I'm driving a car in another county, I get some messages. Too many. Can we profile this? So the OEMs and 5GA came in and decided to start a project, which we deployment guide. Makes sense. What day one looks like. So we want the infrastructure folks to be equipped to give the right messages. That was our initial motivation. Then we talked to the IOs. Hey, we have a different day one. You OEMs can't dictate to us what our day one looks like. Remember, I talked about priority and preemption with emergency vehicles. Then we have an interesting. So we transformed this to be broad, and we defined 3 day ones: IO, OEM, and believe it or not, there's a tolling aspect. You can do if you have this transceiver in your car. Why don't you disrupt the tolling industry? And actually, that's getting ahead of steam. That's a detailed discussion. Kind of fun. I'm saying smile because there are people who are bound and determined to take out the norm, including OEMs. So there is a commercial benefit. Remember, OEMs want to do safety, but they want to see how to do a commercial benefit. So these are 3 separate day ones, and what we did, and this is a lot of detail, but just suffice it to say that we have defined exactly what messages belong to day one. No more. Please stop. So this is basically what the community decided. So you don't congest the channel by advertising and delivering services that no one wants. So that's a profile at a high level. And then all along the while, we're developing what's called ASD, aftermarket safety device, or some people call aftermarket UX device, to fill this. So wearing my hat, I have leaned on all the people who are extensible customers, people who build little boxes. And we've developed the standard, an ASD standard. The idea is to drive it down from a few $1,000 to a few $100 so that it could be widely proliferated by fleets. So this is happening, and we have this. It will take too long to describe them. You can imagine ultralight, kind of what is very, very, not necessarily a safety device, but maybe good for priority preemption. You don't have turning movements. We have light, and you have full, which is a true safety device. So we delineated this in a standard that's in ballot right now. Okay. One more thing before I get into AVs is that sensor data sharing is kind of cool. It starts to get into AVs. So you could think about something on the road user, the roadside. So this is road user, it's a car. Imagine that's a car, and that's the infrastructure system. All that happens in the fusion and how you do the combination doesn't matter. For people who care about radios, what matters is message generation, message dissemination. So we created a standard called sensor data sharing. In the early days, we created it because we thought it'd be really great. We had a bunch of cars that could share data in simplified ways. So we developed a protocol. But imagine it's just the intersection that does the sensing based on its cameras. You start to do VRU protection because so the only sensor data share is the VRU. Is that the intersection, and then all of a sudden you have a scalable system that barely impacts the BSM. We've done some simulations, we want to introduce some standards. So this is a new entry to day one. It starts to address VRU in ways that are technological feasible. I'm not going to go over this. It's got a standard. It is fun to read. Those of you who like to read standards, it puts you to sleep if you're really tired. But the point is that we thought very carefully about how to do sensor data. I'm going to skip the video because I know you guys like videos, but because I don't want to spend all this time talking, I'd like a little bit of question and answer after this slide. So I talk about CVs and AVs, right? I call them different things. Some people call them one thing. So why is that a tough one? So we're trying to figure out how do you get the CAV to work? So those of you who are in the standards, there's something called ISO 26262, which is functional safety. There are other standards that matter too. Just think about functional safety. That means a process standard. That means whatever you have has to be safe, defined by the standards, functionally safe. So think about a telematics piece of equipment, communicating piece of equipment. There's 2 problems. One is that it doesn't go through the same process because that, we're leveraging off handsets, right? So that would be really, really expensive and hard to do. The second thing is that if you're the receiving end, there's exogenous information. Cars are designed to be functionally safe. Everything is contained by the OEM, so they can make sure that process. But how do you handle a signal coming in if you don't know it's functionally safe? So that's a problem. So there are a variety of ways we can do this. It's the redundant sensors, maybe. I didn't make this slide. A French person did, so you see some funny spelling. This is a 5G in itself. You put more safety, rigor into safety engineering. You can do that. You can wait for cooperation from LiDAR or radar. So as you can kind of stage this. Denim is a European standard. Don't worry about that. You can wait for cooperation from another vehicle. You can look for further cooperation from the transmitter of the denim and basic message. You can do a whole lot of things. All these things add to it. Okay. But the ultimate, or you can do SCMS, Security Credential Management System. That is, you can have basically a certificate management system that tries to at least guarantee trust, but still guarantee functional safety. So we're, pulling our hair out. So basically, it's going to be really hard, and there needs to be a lot of work in order to have true connected automated vehicles. What I mean by that is for the maneuver control, throttle, brake, and steering to be actuated off of the radio system. So again, CAVs used a lot by LLOs. I say it's a challenge. So maybe because I'm talking to generally a young group, maybe it's an opportunity to succeed. This is the problem that's in front of us. So the conclusions it's hard. So could have kind of said that. So I think I wrapped up. I've kind of given you the story. Hopefully it's a nonfiction story, I promise you. And I've given you the opportunity of where the challenges are. There's still a lot near term, which I'm dealing with, but hopefully in this audience there are people who can address, solve the long-term problem. So with that, I thank you very much for the time and attention.
Now we can open the floor to any questions to Jim. Okay, there are two questions.
Okay, so you have mentioned that C2X can support the speed of vehicle, something like 500 kilometers per hour, right? So then at that time, because the speed is so high, you have a lot of Doppler shift.
Yeah.
So can LTE or NR signal support such processing of high speed?
Yeah. So so maybe I should start indirect. I'm going to answer you directly. So the question, just for those of you out on the internet, is that does LTE do this and to allow this? So this is yes, your radio in your handset has to work with trains that are coming at each other. So that's 250 kilometers an hour times 2. This is the 500 kilometer an hour thing. But and previous to this release 14, where we are now, and 15 in the US and China, we had release 13 and 12, which is device-to-device communication, ROSE. So basically, we addressed the Doppler by carrier spacing, and then we addressed the packet size, and did a few more fancy things, and that became release 14. And so this was the requirement of 3GPP by SA1, or the requirements group, and RAN, the radio access network standards group from 3GPP, showed that it would work. Now, this is an extreme case. On US highways, you're not going to get there. But that's an old slide, but that's the history of it.
So you mentioned, and thank you for the great talk. You mentioned that C-V2X may or may not be like 5G compatible going forward in the future. And that made me curious, do you foresee there being any kind of limitations of future innovations by kind of setting everyone up with this as the standard?
It's a great question. I did promise that I talk about that, and I didn't. So you're forcing me to talk about it. So, we're approaching release 18, 19 now. We're talking release 14, 15. If you're doing Sidelink, the 5G was in release 16. So what's happening? You might ask. Couple of dynamics. One is we don't see market demand, partly because there's not enough spectrum. Because if you imagine two things about 5G video Sidelink is one is that you can have higher data rates. Very nice. Second is that you have this connectionless broadcast. So what does that mean? That means only, you can do it by distance, so distance-based group tests. So only those UEs, devices that are relevant to me by distance. So imagine cars platooning or cars approaching the intersection. It's pretty good because the other cars don't matter. So then you can have sessions, not ad hoc. So that's really good for project merge, all sorts of cool things. But you need spectrum because you basically have a dialogue of acts and acts. And so we're not there in North America. So, but think about this, is that if you have a safety system that does something, you can't say, well, I'm going to rip and replace it in a few years. That won't work. So if this becomes a market force, it's going to be here for 15 plus years. So there are various reasons why it's not going to happen.
What's so special about 5.9 gigahertz?
Well,
For example, why not use the radar bands that which almost all
77
cars-
gigahertz, you mean? It's hard enough to do cabling and antennas for 5.9. Think about it. But people do it for radar, but it's already used for radar. The 5.9, you have some great questions. So ever since I started to work on this in the 90s, we petitioned FCC for 5.9, I think because it's the spectrum that was available. It has certain good properties. Toyota has something called ITS Connect in Japan, which I think works at 9 megahertz band, 760 megahertz. And they say it's really good for a built environment because you go through buildings. So you don't bounce around curves, you go through buildings. But for various reasons, and some of it legacy, that's what we settle on. We're working assiduously through WRC, or basically how we get spectrum allocated globally to make this happen. It's good to have one SKU, at least at the radio level, right? The application protocols is just software. So that's what we're trying to do. Any more questions?
I might take this advantage to ask a question.
Sure.
And I get asked a lot of times by my students during my class. It's generally for V2X. Jamie, your expertise, what do you think will be the major hurdle to deploy V2X in our cars? It's more like with technology constraint, legislation constraint, or like different stakeholders, they have their different conflict of interest, like different OEMs and different tech companies. What do you think will be the major hurdle for us to all have V2X?
Those are all major hurdles. This is why it's not happening quite yet, but we can be optimistic that it's happening. We see the momentum. Frankly, the biggest hurdle is cost. And you know, we're not talking much, but again, you want to buy a car that doesn't cost $100 more. You start to look at that, and the car OEMs know that. But let's get around that because the safety benefits are prevailing. Right? The other hurdles have been, hopefully past tense very soon, FCC, spectrum regulation in the US. And the other major hurdle was money. As I said to some of you before, sorry to be repetitious though, my first boss said, "You want Buck Rogers, you need the bucks." And so, but we start to see a little bit of that with DOT and other governments. In China, they're overcoming a major hurdle, which is a mandate. So there's no mandate, but there's something called NCAP. So many of you know what NCAP stands for cars. So it's part of the NCAP scoring system in China. So there are other different hurdles in China I don't want to belabor. One of them is obfuscation of the vocation for national security. So every region has unique hurdles. But again, to overcome the regulatory, the spectrum, standards are largely overcome. Some people will argue that they want to do standards forever. Those are the hurdles.
And since your talk is about V2X and on, I just want to ask this million-dollar question. Which one do you think will come earlier?
Oh,
It's vehicle automation or vehicle connectivity?
you can ride a Waymo in various places, right? So,
I mean, say 50% penetration rate.
Great question. So, you know, I am talking about automation because that's the end point, but notice I didn't focus on it. I just show how hard it is to combine the two. But if you're talking about connectivity to a network of babies, obviously you need training data. You might do it offload with Wi-Fi with the garage, but whatever, you need that. So that's our connectivity is already established. I work for a big company. I'm not an entrepreneur, so I can't predict what the market will be. If I would, I might not be standing in front of you. I might not. So I can't predict. But you know, perhaps other lecturers will come invited seminar speakers will come and talk about the challenges of getting into automation and some of the fatigue that people experience. But let me just tell you something that is very bright. ADAS is here. And so if you talk about SAE 20, 30, 60 levels of automation, level 1 and 2 are for sure. And so you can argue that automation, lower levels of automation, is happening in virtually every group.
Oh, can I ask a follow-up question?
Sure.
So Jim, with one follow-up with that question. Then do you think connectivity is a necessity to high-level automation, or it's just an option?
Well, I can tell you what I think, but that doesn't matter as much as what the AV companies think. So certainly connectivity, as I described earlier, network connectivity is important for so many things. You update your maps, you do all sorts of interesting things, you train. Connectivity, so for example, let me use the eyes and ears. If you have eyes, you can maneuver pretty well. If you have ears, you can do a little bit better. So I would suggest it's an enhancement, but an essential enhancement. Now, you've heard stories about emergency vehicles approaching AVs in some cities, right? The fact that they can't communicate. And there's actually standards activity using 19th century technology, putting lights on it, right? I think you should put a radio. So it could enhance. But that automation juggernaut, I would suggest for good is happening. But the ADAS is here to stay. And certainly we are striving to make CV2X cousin, maybe not that related, but cousin of ADAS to really add that extra benefit for safety. Yes.
You mentioned earlier, building up to like 85% of, say, intersections in the top like 75 metropolitan areas. What is the average cost per intersection? You see that coming down? Do you see this being
yes, I do
for the non more like the rural areas?
So these are great questions, and it's not just the capital costs; it's the OpEx or the operations and maintenance costs that we have to worry about too. But the preponderance of the cost is the truck roll and the lane blocking. And so it's human labor. You don't want to place that in a job. So that's the preponderance of the cost. The device cost, we're doing our level best to drive that down through the ASD and through standardization. The beauty of that is that once someone has something standardized, it's not unique, and it starts to drive the market cost down. But right now, depending on who you talk to, and I guess it might be more expensive in California than Indiana, right? It could be anywhere from $10,000 to $15,000 an intersection, sometimes more, sometimes less. So yeah, it's significant. This is why we get numbers that add up to multiple billions of dollars if you were to make this happen nationwide.
Kind of just a follow-up to that question. Do you foresee there being like a higher maintenance cost associated with intersections or stretches of highway that have these
So what you're doing is that I love DOTs. Berkeley, Caltrans funded a lot of it. But I understand their challenges. So one of the challenges is a workforce, and they have to compete against tech companies for the workforce that has a sophistication. Often in ITS in general, you see a lot of capital investment, very little operations investment. So there needs to be a shift in understanding. Creative ways of doing maintenance and operation. Some of it would be contracting out, but that's not necessarily cheap. But yes, I'm not painting a yellow brick road. I'm painting hopefully a road that has promise, but there are still problems that need to be addressed.
Thank you. Thank you very much, Jim. Let's thank the speaker on the time. Students, feel free to hang around with you, ask any questions regarding career opportunities and so on.